All right. Hey everyone, my name is Ishan. I currently work at StackAV and I used to work at Argo AI. So I'm going to take away the presentation for the Argoverse competitions for this year. Okay, so just a quick outline. We're going to talk about what Argoverse is, the current status of it, and then we're going to go over the three challenges that we have for this year, which are unsupervised scene flow, which Deva kind of already talked a little bit about, the scenario mining challenge that he also advertised for us, and then multi-agent forecasting. So just really quick to refresh everybody, Argoverse is a collection of 4 datasets that was gathered by the Argo AI autonomous vehicles across 6 US cities. We have the sensor dataset, which consists of LiDAR, camera, HD maps, and 3D cuboid annotations for over 30 classes. We have the LiDAR dataset, which is unsupervised, unlabeled LiDAR point clouds from 20,000 scenarios, with 64 beam LiDARs. And so this is useful for self-supervised training. And then we also have the motion forecasting data set. This is over 250,000 scenarios, vector maps, and then object tracks for 10 object classes. And then finally, we have the map change data set, which contains LiDAR imagery as well as vector map data. And this is specifically focused around scenarios where the maps have changed specifically. So yeah, if you want to get involved and use this data for any of your challenges or participate in our challenges, please feel free to check out the Argoverse user guide. We spent some time and effort, Ben specifically, to revamp this in the last year, and hopefully this is a nice API to use the data. And so then just really quickly to kind of touch on the state of Argoverse, again, after Argo, which has shut down like over 3 years ago at this point. It's a community-led effort. So all of us who are kind of hosting these challenges and participating in them, this is all driven entirely by the community. And we actually were able to launch a new challenge this year called scenario mining. So that's just a testament to how strong the community is and the fact that the data set is still being supported. And we welcome any ideas or support from you guys. So please feel free to check out the API, submit a pull request, or contact us if you're interested in hosting a challenge or using this data in some way. There's already been kind of various data sets like OpenLane and stuff that repackage the Argo data to be used in other challenges, and that's really inspiring. Also, I'd like to thank Amazon AWS. Their open data set initiative has been hosting Argoverse since its inception, so we're very grateful to them for that. Okay, so quickly to talk about scene flow. I think Deva already mentioned about this stuff in his previous talk, so I will try to be brief. But obviously, we care about motion. We want to know what objects are moving and how they're moving, understand the world in that sense. And so, scene flow is this kind of per point association of what points are moving, between consecutive frames of a LiDAR point cloud and how they move. And so, in order to get labels for this, we are using the Argoverse 2 sensor data set, which consists of these 3D object tracks. And so we can, associate the points with the bounding box that they're within, and then apply that motion, to those tracks. So if that looks something like this, we have 2 bounding boxes and 2 different time steps, and then we associate them using the tracks that are provided by ground truth, and use this to get the scene flow labels. I think Dave also mentioned some of the problems that can arise with scene flow, and so I'll talk about how we kind of tailor the evaluation metric to solve these challenges. And so if you're familiar with optical flow, you might be thinking that average endpoint error is a good way to measure the error here, and that was the traditional metric for scene flow a long time ago. It's also used in optical flow, but there's a problem with this, which is that average endpoint error is dominated by points that are in the background which don't move at all. And so it actually turns out that like over 80% of the points are background. They're static, they don't move, and so it's very possible to get very good average endpoint error because you're averaging by just ignoring all the moving classes, and so just predicting zero flows. So you want to do that. So in order to resolve this problem, there was a paper here by Shodash and Deva and some other people, which proposed three-way endpoint error. And that is a breakdown of all of the points in the point cloud based on whether they're static, dynamic, or in foreground or background. And that allows us to compute a little bit better error. And so this was the predominant metric for the previous scene flow challenges with Argoverse 1. However, even this has problems. Again, Deva kind of like alluded to this and pointed out some examples where it turns out that the foreground classes are still, all the points are dominated by these large vehicles, and pedestrians and other vulnerable road users, they make up less than 1% of the data. And so you can see that it's possible to get very good three-way endpoint error and still ignore all the pedestrians, and that's really bad. Resolve that. Okay, so here, this is the same thing. We can see that we have issues. A lot of these state-of-the-art methods have issues with pedestrians and detecting and following them. Okay, so the metric we came up with to resolve this is called bucket normalized endpoint error. And what we do is we basically take all of the dynamic objects and we bucket them into the classes that we already have from the ground truth labels. And then in addition, we also normalize all of the flows based on their velocity, the average velocity of that class. And normalizing is important because it allows us to compare error between the different classes. So we can know that like error is now a percentage, and we have 20% error on pedestrians versus like 10% error on cars. And that allows the metrics to actually be comparable, because if there were absolute values, cars that move much faster, they would have a higher error, for example. Okay, so that was an overview of the metric, and obviously we used the same metric last year as well for the challenge. So we've had incredible progress in the last 1 year. So here's the state of the leaderboard as of like yesterday when I took the screenshot. So you can see last year's methods are like near the bottom of the leaderboard. So the one, let's see if I have a pointer. Okay, right. So this was the supervised track winner from last year. And you can see that we've already surpassed it with a bunch of other supervised methods. Here was the baseline. This was the method that David talked about, where we use the tracks from an object detector. And then down here was the unsupervised challenge winner from last year. And so you can see there was a lot of new entries, and a lot of progress has been made. So with that, let's kind of talk about the supervised winner for this year's challenge, which is DeltaFlow. And they have a GitHub repo here, so you can check out their code. So the key insight of DeltaFlow is that temporal fusion is very expensive. And so what they propose is using features that are actually a delta of the previous time steps feature instead of concatenating a bunch of brand new features for every time step. So what does that look like? Well, traditionally, in a temporal fusion pipeline, you would have multiple point cloud frames. You would then kind of compute features over those point clouds with like a voxel grid or something. And then you can see here, you might concatenate them together to build one big feature. Or you might do some kind of like 4D temporal convolution thing and then try to build a four-dimensional feature this way. And these things are all very computationally expensive. So either you're going to be expanding the amount of memory you need on your GPU by a lot, and then also increasing the size of the feature tensor, so more computation, or you have to do this like 4D convolution, which is also very expensive. And so what they propose instead is computing these delta features. So they take the feature maps at every time step and they subtract the previous features, and then using the delta time step, the delta scheme, they're able to kind of get one final feature map that's used as input to the model. Okay, one other thing that they did in this paper is they also incorporated a category-based balancing loss. And this is really interesting because I remember in last year's challenge, we actually suggested that somebody should do this, and we were surprised when none of the entries had done it. And so, DeltaFlow did include this, and it gives a nice 3 to 4% boost on pedestrians and vulnerable road users, which is very nice. So, the other really cool thing about DeltaFlow that they did is they also did cross-domain experiments. So they actually trained the model on Argoverse and then tested it on Waymo and vice versa. They trained it on Waymo and evaluated it on Argoverse. And I guess technically, based on the rules of the challenge, that counts as an unsupervised entry because we said you could use pre-trained models from other data sets. Although I think it was, not really in the spirit to use another scene flow data set. We were more hoping for like RGB or other foundation models. But it is a really cool experiment. And so with that, I will then transition into the unsupervised track. So again, this is the state of the leaderboard. It turns out for unsupervised methods, our own Euler flow is actually still state of the art. No one has turned out to beat that. But I instead want to highlight another method that is at CVPR this year, which is just as good. Like it is very close. It is Floxels. And so Floxels has the performance that is like, a few percentage points of Euler flow. It's very close, but it solves the runtime issues that David was talking about in his talk when he mentioned it. And so this is really cool because what they do is they apply the trick that has already been applied to nerfs. Right? So we talked about how neural scene flow prior is basically a deformable nerf. And so in nerfs, what's common to speed them up is to just use a voxel grid instead. And so Floxels takes some of the ideas from nerfs and some of the ideas from Euler flow, and instead of using this like MLP neural prior, it uses a voxel grid to optimize instead. And this gives them like incredible speed ups. I mean, it is 100 times faster than Euler flow. It's not real time. It's still kind of in the realm of a test time optimization technique, but it no longer is going to take you like 24 hours to get really good scene flow on a single sequence. So there's some other advantages with this as well because they're doing local optimizations with this voxel grid. There's less background artifacts and better convergence dynamics. So you can see that in this. And then, when it's used for kind of point cloud accumulation, you can see that the background artifacts kind of go away. compared to MLP-based methods. And this is really valuable, for getting very clean scene flow and accumulating moving objects in a point cloud over time. All right, so this is really cool, and that's all they have for scene flow. So I'm going to hand it over to Nihar for scenario mining.
Cool. Thanks, Ishan. Okay, so as Deva briefly touched upon, we wanted to explore the problem of scenario mining, and this is broadly motivated by the fact that autonomous vehicles are out there in the wild right now, and they're collecting terabytes of data. And most of the data is not very interesting. So as you might imagine, everything that you see in the wild follows a long tail distribution. So it's really quite a challenge to find the interesting and safety critical scenarios in your sort of treasure trove of data. You need to sort of sift through all this information to find the interesting things to train on and eventually test on. So this was sort of the motivation for this challenge. One sort of thing to note is that this challenge is not really operating in a vacuum. It's very similar to other efforts in the community. So it's very similar to referential multi-object tracking, which, given a natural text query, you want to find the associated object and track it over time. But different from prior instantiations of similar challenges, we're mostly interested in interesting multi-agent interactions. So if you have a whole bunch of agents in a scene, how do they interact with each other, and how does this actually translate to interesting and safety critical behaviors? And just to sort of call out, this is almost the inverse problem of scenario generation. So this is another challenge which I think the Waymo folks will talk about later this afternoon. So to study this problem, we curated a large-scale data set, which we call RefAV, and this is towards the goal of building planning-centric scenario mining benchmarks. So within this data set, we have interesting scenarios like a passenger vehicle near a stroller on the road, or pedestrians walking between two stopped vehicles. Similarly, we have things like a bicycle passing between a bus and a construction barrier, and then an ego vehicle approaching construction zone with a traffic controller. So these are all sort of interesting multi-agent interactions, which are sort of not obvious on the face of the types of labels that we already have within the Argoverse dataset. So importantly, we had to derive these labels from the existing sensor dataset annotations. So the problem set up here, as I mentioned, is very similar to referential multi-object tracking. So you're given a natural language description, like find the vehicle stopped in front of a jaywalking pedestrian, and you're given rich multimodal sensory inputs, like an HD map. You have a LiDAR point cloud and an RGB image, a set of RGB images. And it's important to note that this is an offline challenge. So you have all the sensor data for the entire log sequence. So you can run your very expensive off-board perception models to really reason about the contents of this log. So the challenge is really parameterized to find interesting scenarios within a 50 meter by 50 meter range. And we're mostly looking at multi-agent interactions between the 26 most frequent categories labeled within the Argoverse 2 dataset. So this sort of gives rise to this problem of spatiotemporal scenario mining. So given an example of a vehicle making a left turn through the ego vehicle's path while it's raining, in green here we have the referred object, so that's the vehicle, also shown in green on the visual there. In blue we have the ego vehicle, so that's related to the prompt. And then in red we show all the other objects in the scene, which are sort of useful to detect, but not necessarily relevant for this particular scenario. So the way in which we go about evaluating models on this benchmark is through tracking-based metrics. So I just want everyone to recall a very popular tracking metric is HOTA, higher order tracking accuracy, which decomposes tracking into its different components. So you have a detection component, an association component, and a localization component. And HOTA basically combines all these together to create a single number that describes how well your tracking model performs. So we tweak this slightly, and our primary metric is HOTA temporal. So it's exactly the same thing as HOTA, but now we only consider scenario relevant objects during the precise timestamps when the scenario occurs. So instead of tracking all cars, now we're just looking for the timestamps when the car is turning left, for example, if that's the prompt. We look at a couple of other retrieval-based metrics. So this is more in the spirit of traditional scenario mining types of metrics. So the first metric we look at is log balanced accuracy, and this is really a log level classification metric. So can your method accurately determine whether at a log level you can figure out whether or not the scenario actually happens? Similarly, we have an extension to the timestamp level. So we have this timestamp balanced accuracy, which is basically looking at every timestamp, can your model correctly identify whether or not the scenario is actively happening? Okay, so now given all of these metrics and the setup, we propose a interesting baseline which leverages all the recent innovations in large language models. So we propose a two-stream approach where in the first path we have multimodal RGB and LiDAR, which is processed by a sort of slow offline 3D perception model. And this gives us 3D tracks for all 26 object categories. And we also use an LLM through program synthesis that takes a natural language prompt and turns this into a generated code snippet. And using this code snippet, we can then go and filter the 3D tracks, which we get from our offboard perception system, and then figure out which tracks are being referred to, which tracks are related to the referred track, and what are all the other things in the scene that we don't necessarily care about. So this approach has many of the typical failure cases that you might expect with large language models. So not considering the limitations of the offboard perception system, we find that our baseline, which we call refprog, struggles with semantic ambiguity. So in this case, we have a car following closely behind the bicycle, but the generated code snippet from our LLM is actually inverted. So it's actually finding the bicycle that's closely following the car. Right, and we also have this limitation of a lack of expressiveness. So given the query, find a car pulling out of parallel parking onto the road, the sort of API which we define to be used by this large language model simply doesn't have the expressiveness necessary to find such interesting and complex scenarios. And I think these two limitations were a huge motivation to the winners of this year's challenge, who basically took this to heart and really tried to figure out ways of improving upon the limitations of the LLM. So this is a quote from one of the team's technical reports. The limitations of these LLMs are not merely superficial issues, but represent fundamental hurdles in reliably converting complex human language into precise and correct machine executable instructions. So I think this sort of very nicely illustrates that these are sort of fundamental problems that we as a community need to wrestle with if we want to bring to bear vision language models for the task of scenario mining. So to announce the winners of this challenge, we had 8 teams participating in this brand new challenge with over 100 submissions. So I think this is an excellent showing from the community. And I want to highlight a couple of interesting takeaways from each of these methods. So the first place, I also want to highlight that all methods adopt our sort of proposed program synthesis-based approach, and they propose tweaks to improve the performance of the LLM. So all models take as input the output of an offboard perception system proposed by a team that participated in a previous iteration of our challenge for end-to-end perception. So this is offboard tracks from team LE3D E2E. And these were state-of-the-art tracks, so it's natural that we want to use these for this challenge. So the first team, Zeekr UMCV, has 2 key insights. The first insight is that instead of asking the LLM to process each natural language query one at a time, it turns out that LLMs are sort of great at reasoning about long context. So if you prompt for all of the classes for all of the sort of natural language queries all at once, your model is able to sort of reason about the sort of regularity of prompts and figure out how to appropriately turn everything into sort of nice executable programs. And the other sort of almost intuitive insight is that if your LLM generates code which doesn't compile, the most natural thing you can do is provide the sort of broken code and the error message back to your LLM and ask it to come up with a better prompt. And it turns out that these 2 techniques are sort of pretty important to improving on our baseline performance. So importantly, I'll sort of quickly go through the other methods because it turns out that all of the top teams had similar ideas. So the second team, MI3 UCM, also leverages this key insight of iterative prompting. The third place team, ZXH, leverages this idea of batch prompting. I do want to sort of give an honorable mention to team DGIST that not only sort of uses reasoning LLMs. So in our baseline, we use Claude 3.7. They swap this out for the O3 reasoning model, and they find that this reasoning capability seems to help a bit. They also use a VLM to help with this iterative prompting. So instead of just passing the generated program back to the LLM, they also pass in RGB images of the scene, and they use that to figure out how to best tweak the generated function. Okay, so with respect to this challenge, I think in the next iteration, we'll want to increase the dataset size, make things even more diverse. But from the method side, it'd be great to see more end-to-end approaches. As I mentioned, our method struggles with a lack of expressiveness. So being able to, on the fly, generate an API to construct more informative programs would be great to see. And I think one of the key challenges is that in the real world, we're dealing with terabyte scale data, and it's incredibly important to consider runtime. So if we want to really scale this up to terabytes worth of data, we need to be cognizant of compute bounded inference. And lastly, let me quickly go through the results of the multi-agent forecasting challenge. So we've been running this challenge for about 7 years. And in every iteration of this challenge, we've innovated on the evaluation setup, improved the ranking metrics, and every year the community has sort of impressed us by continually improving upon the final performance of the model here. So just to recap, this data set is collected over 6 cities with 250 scenarios, and it's highly curated to be challenging. So we have AV relevant interactions, socially complex environments, and many non-vehicle actors. And let me sort of skip through this. This iteration of the challenge really focuses on multi-world forecasting. So in order to safely plan, one key insight is that we need to understand how not only how we move, but how everyone else moves in the world. And we need to think about how this occurs jointly. So this multi-world forecast actors. So the input here is 5 seconds of kinematic history. We know the sort of class types of all the actors, and we have a local static map. And the task here is to predict normalized probabilities for 6 futures that captures the joint probabilities of how all of these agents interact with each other. Okay, so I'll sort of briefly skip over the metrics here, but the key thing to note is that lower is better in this case. Okay, so we had over 100 submissions from 26 teams, and we had many people submit to many of the Argoverse 1 and Argoverse 2 leaderboards. And what we found was that the best performing team, IMR, which is iterative multi-world weighted regression for multi-target trajectory prediction, was one of the only teams that improved over last year's top method. So huge congrats to this team. And they were able to show a 5% year-over-year improvement on the primary metric, which we used to evaluate, which is min-world Breyer FDE. And sort of to briefly talk about the highlights, they propose an iterative decoder with segmental refinement. So this means they basically break up the 6-second future trajectory into 3 components. They predict the 0 to 2 second trajectory differently than the 2 to 4 second and 4 to 6 second trajectory. And then they perform temporal attention and perform this prediction iteratively. So this temporal attention leverages the initial set of predictions to inform the next iteration prediction. And they also propose a mode world weighted regression loss, which encourages mode diversity while preserving top 1 joint accuracy. So that was a quick overview of the motion forecasting challenge. And again, we want to sort of urge the community to think about forecasting under bounded compute. And as for the Argoverse 2 data set as a whole, I think there are a number of interesting directions that we as a community can go and move forward. And as Ishan mentioned, it's critical for the community to step up and get involved. So I think this is a great opportunity for folks in the community. So I'll end with the last note that all the challenges we talked about today will remain open. So we talked about unsupervised scene flow, scenario mining, and multi-agent motion forecasting. So if you're interested in any of these challenges, please feel free to submit. And if you have any questions, the Argoverse to GitHub is a great place to post an issue and ask your questions. So with that, I'd be happy to take any questions. Thank you so much.